Gentlemen, thank you.
Great to be here.
It's good to see you both. I want to start by saying that observances of 50-year anniversaries are a big deal in our culture. Just a couple of years ago, everybody was buzzing about the 50-year anniversary of Moore's Law,
Yep.
which you had a thing or two to do with.
Yeah.
Well, there's another 50-year anniversary that I want to focus on, and that is the publication of a book, turned out to be a very seminal, important book by Alvin and Heidi Toffler called Future Shock. And George, I understand you had some experience with the Tofflers.
I did. Future Shock was exciting, but I think the third wave was their masterpiece, and it really did anticipate much of my work. So it really was a prophetic kind of sweeping take of futurism that I think excelled Future Shock. The third wave really did capture this whole information inundation that the world experienced, information flood, and dealing with it and transforming it in us.
Speaking of this notion of a rapidly advancing future, which is really what Future Shock was about, it can be explained, at least in some sense, in part by Moore's Law, right? Which it had a tremendous impact on modern society, perhaps more so than any other foundation technology. Yeah. And you, of course, were at the center of that, if not pivotal.
That's true.
And it started out quite simply. Gordon Moore asking you a question.
Yep, that's what happened. Yeah, I remember I was consulting for Fairchild at the time, and Gordon's an early morning person, and I'm an early morning person, so he would get into the lab up at Fairchild, which was in Palo Alto at the time, and he'd get in early, and I would be up. I would fly in the night before and do my consulting day up there. And it was always the same. I'd come to his office and he'd be the only one around. And so we'd get about an hour before things got busy. And I walked in one morning and he said, "What do you think of this?" And it was a picture of the plot of the complexity of the chips. And he had one picture for each year. And he had put a line through them, which of course was an exponential increase. And then he just dotted line from that. And I said, "Wow, that's pretty neat." And he said, "Well, you're working on electron tunneling, aren't you?" And, "Yeah." And tunneling happens when things get small. "Yeah." He said, "Well, won't that limit how small you can make a transistor?" And I said, "Yes, it certainly will." And he said, "Well, how small is that?" So the only thing I could say at the moment was, well, the transistor gate, the input, the transistor, can't start drawing a lot of current, or you can't use it as an input anymore. And it'll start drawing current when the gate oxide gets down to, I thought I had worked with gate oxides, and maybe 50 angstroms was getting pretty thin. Well, that was very conservative, but it gave us a start. Mm-hmm. And then we went and worked out how the whole transistor would scale and all of that. But that was 1965. That was a very, very interesting year. No,
Carver named Moore's Law, though.
Yes.
That was a crucial.
Well, what else could you name it? Because nobody believed it. They had all kinds of reasons why you couldn't make transistors that small, so we had to work out. No, that works with all the physics that we know. But it was a tough sell.
Yeah.
And Gordon was pushing the economics of it, because obviously if you can make them, it's a no-brainer. This will change the world.
Right.
So of course everybody hid behind, well, but they'll never work. It's maybe another factor or two, but then this or that or the other physics will get you. Mm-hmm. So we had to go back and work out the physics and point out that it wasn't going to get you if you did it right. Mm. And so that was probably 10 years fighting that battle.
Yeah. You finally overcame the energy barrier.
Yeah, yeah. You need a critical mass. Yeah. And then it's groupthink. And it goes from groupthink, oh no, it'll never work, to groupthink, oh, yeah, of course we'll do that. It's amazing.
And it projected billions of transistors on a chip, the world we live in today.
Yeah. Mm-hmm.
At the time, it was assumed that as you scaled the transistor feature sizes down, the performance would be significantly degraded, but just the opposite happened. They did in fact get better, faster, smaller, cheaper, and because the power density per square area remained constant.
Yeah, but
they were cooler.
That little scaling law took me 3 years to figure out. Mm. And I gave a talk on that in one of the device physics workshops in 1968.
The Ozarks, right?
Yeah, Lake of the Ozarks.
Lake of the Ozarks.
And one of the people there was Bob Denard from IBM. Mm-hmm. The guy that gave us the modern version of the dynamic RAM.
Right.
Very smart fellow. And all of the people there were giving me a terrible hard time because it couldn't possibly be this good. There was something wrong with mine. Mm-hmm. So we had a big argument about that. But you could see that Bob he wasn't just fighting about it, he was thinking about it. So at the device physics workshop the next year, the Navy used to put these on. And the next year he had his own version of that, which was pretty much like mine. Mm-hmm. And so now there was an industry guy.
Oh.
And so then, and at that time IBM was a big name still. So it weighed in, and I think that may have been a turning point.
And what year was that? Do you recall?
69.
That was in 69, okay.
Yeah.
And that became Denard scaling.
Exactly.
Yeah.
So in 69, in 72, you had predicted that transistors could be made as small as 0.15 microns. And that...
we actually worked out real transistor designs, and, because other than that, people were still sort of quibbling about what you do. So we worked out all the details.
Yeah.
And that helped.
Okay. Well, since hitting that mark in 2000, we've blown by that estimate by an order of magnitude now today.
Oh, yeah. Well, what we said was if we did nothing different, used the same gate oxide, we used the same structure, we used silicon substrates, we used silicon gates, we did everything exactly like we're doing it then, and all we did is shrink all the dimensions. Then it would scale like this. Mm-hmm. And you would start getting in trouble at, 0.15 microns.
I see.
And it turned out that was just about when they had to start doing fancier things.
Yeah.
The processes got more complicated, and they started looking for
that was a hinge.
High dielectric constant gates, and they had to start getting much fancier. But it got 20 years, so that was...
And another order of magnitude,
Yeah.
It's pretty remarkable.
So we had that pretty well right. Mm-hmm. We didn't speculate on, suppose you do fancier things. Obviously you could do fancier things, but they're not going to worry about that until they get there.
The question that occurred to me was whether this was just another learning curve. The learning curve was one of the most thoroughly documented phenomena in all technology and
Yeah.
business. And it ordained that with every doubling of total units, you got a 20 to 30% drop in costs. And learning curves slow down at a certain point because you got to get fancy, and it takes longer to double the number of total units. But it seemed to me that Moore's law really was about the learning curve in transistors. And now we've got learning curves in lines of software code and insurance policy dollars and trucking miles and eggs, poultry, and just about everything, and project it into the whole economy as a learning system. And that's really what I've been doing in
Yes.
recent years. But it all began with Carver and
Right.
me meeting Carver way back.
Yeah, tell me about the occasion of your meeting.
Well, I was writing, I went to Ben Rosen, who wrote the Rosen Electronics Letter. And after writing Wealth and Poverty, which was a big worldwide bestseller that made me Reagan's most quoted living author, I decided that the most important thing in the world was microchips. And I actually showed Reagan his first microchip. I showed him a Micron 64K DRAM. I went and,
Oh, is that right?
and explained how this would make possible SDI and all those ambitious technologies that he wanted to build. And so that was, and I wrote a book about Micron way back in the day before it really emerged. I wrote the story of Micron called The Spirit of Enterprise. But anyway, it seemed to me that learning curves are the most fundamental fact in capitalism. And Moore's law was the most important of all the learning curves. And I think that the convergence of Santa Fe Institute has recently done a paper that's demonstrated essentially that Moore's law and learning curve theory both converge. They are really the same phenomenon. So that was an intuitive idea I had, but Santa Fe Institute now says it's real mathematically, which is
Okay.
kind of certifies.
There you go. Right, there you go. So I wonder if there is a shadow side to Moore's law. Alvin Toffler did not mention Moore's law specifically, but he certainly described its effects. In particular, he wrote, "Advancing technology makes it possible to improve the object as time goes by. The second generation computer is better than the first, and the third is better than the second. Since we can anticipate further technological advance, more improvements coming at ever shorter intervals, it often makes hard economic sense to build for the short term rather than the long." What impact does that have?
It certainly has become less, in my own experience, it's become less common for companies to build for the long haul than it was when I was 50 years ago.
That's right.
When you had companies making research labs to, look forward, and that is not happening today. The short-term competitive nature of things is much more aggressive than it was 50 years ago. And I would say that your quote is a good quote, but in the rapidity of evolution of technology has made the competitive landscape such that the people that did the next thing faster won out over the people who looked further in the future. And in fact, there's been a lot of discussion, well, with Moore's law slowing down considerably, is there going to be a change in that whole nature of whether it pays to look further or not? Because right now, the last, I'd say 20 years, the people who are looking for new technologies were beat out by the people who just use the next generation Moore's law and just use it like it is and don't fool around trying to do something new. Just make the faster microprocessor and the faster memory and lower cost, and you'll beat out anybody who's trying to look further in the future. And that's a very interesting phenomenon that I've experienced personally. And I don't have a judgment to pass on that. Just that's been my observation.
I just think it's interesting that there's this talk of Moore's law slowing down, yet at the same time, we live in what's being characterized as an exponential age, a time of exponential technologies.
Well, it seems to me, feels like, what's really happened is people are very rapidly applying what's basically a not very rapidly evolving technology to new applications in a very rapid rate.
Yeah.
And that the innovation has gone that way, largely. There's an exponential increase in taking advantage of what was really a very nascent technology. And if you look at it, at the applications that have grown out of that, we wouldn't have imagined a tiny fraction of them. But you've seen that closer up, George.
The reason I focus on the third wave, which I think was an amazing prophetic vision by the Tofflers, is that I think Future Shock was wrong. Future Shock essentially said that the information revolution was more profound and more exponential and more shocking than any previous sort of experiences of humanity. And I think the Industrial Revolution, the steam engine, the looms, the emergence of factories, the whole convulsive transformation of the world that happened in the 19th century was more radical and more shocking, wrenching people off farms, plunging them into dark satanic mills, as they were called, moving them into cities, transforming cities, bringing the power grid, which Carver is the world's leading exponent of the miracles of the power grid. I just think it's fundamentally wrong that Future Shock, it was a formula that allowed them to describe lots of real things, and it was a wonderful book. But the fundamental claim that this was new, I think, was wrong. After all, Henry Adams, in the Education of Henry Adams, expounded what he called the law of accelerating returns, and he had all the charts for energy and coal, all based on coal, and from whale oil to coal, and the same learning curves that could have been called Adams' law. And so I think that we're continuing to innovate, that the learning curve is fundamental, and I think learning is the best definition of economic growth. It's not just something that applies in universities or in laboratories or even just in technologies. It defines what economic growth is. Wealth is knowledge, growth is learning, the increase of knowledge.
Okay. So that said, Carver, I think perhaps the least talked about aspect of Moore's Law is, I believe, the most important. You said the Moore's Law thing is really about people's belief in the future and their willingness to put energy into causing that thing to come about. It's a marvelous statement about humanity.
That's certainly the way I have always seen it.
Yeah.
And the way I experienced it was, I think I described already, that it went from nobody believing it was possible.
Yeah.
And it felt like it could take the rest of a person's working life and they still wouldn't believe it. And then at one point it got to be okay, and then it took off. So I suspect it was like that for all of these technologies. I suspect that when someone, well, I know for a fact that when people were saying we're going to replace all of that steam engine and the belts and wheels and all that stuff with these little wires from this place, you know, down on the river, they thought it was nuts. And I'm sure it had the same.
Electrification.
Yeah, electrification was you know, not taken in easily.
No, it sure wasn't.
It was a huge, huge potential barrier, as you would say, to get. So I think any of these things has its own barrier to get into the belief system of our culture. And if you don't do that, you simply don't get there.
Right. Well, and every time there's been a major technological advance, everybody cried, this is going to be the end of society as we know it, right?
Yeah.
And, I mean, and today we're seeing that with the advent of AI, right? But we've always seen exactly the opposite through history.
Yeah.
Would you agree?
I could certainly agree. You know, the whole idea that that technology destroys jobs is ignorant on the face. Technology never destroys jobs. People don't get employed because they're unproductive. AI and like all other technologies enhance the productivity of human beings and make them more productive. And at the same time, yielding capital to endow new work. So, AI isn't any different from any of the other great advances in technology over the years, and it's an evolution of all the original robots and electrification and more intelligent manufacturing, and it's just a continuation. It's not especially apocalyptic, or as Elon Musk says, it's the end of the human race.
Right.
Elon's a great entrepreneur, but he's not a great philosopher.
It's interesting. Almost every one of these new technologies has been resisted by the incumbents. And there's one exception to that. That new technologies introduced into farming have been accepted instantly. And the reason is the farmer is the one that doesn't have to break their back anymore. And they're the ones that want the thing.
The labor-saving device.
Yeah.
Yeah. So it was Max Planck who said, science proceeds one funeral at a time.
Yeah. Yeah.
Right. You've experienced that firsthand.
Oh yeah. Oh yeah.
Carver's transcended an awful lot of funerals with a whole succession of scientific advances. I think that's a grouchy old Max Planck complaining about his associates, but I don't think it captures what goes on in Caltech.
Moore's law has led you into some other interesting areas. In one sense, it shouldn't be surprising that your work in semiconductor device physics would lead you into other areas of physics. So there's a natural interest there. Presently, I understand you're pursuing what could be called a new interpretation of physics that's seeking to unite quantum mechanics and electromagnetism.
Yeah.
What's that about?
It turns out it's always been true that electrical technology of any kind is about electrons interacting with other electrons, sometimes at a distance, sometimes close up, but that's what it's about. And electronics is a name that got attached to the more recent stuff. But actually, it's been electronics since the beginning, since before they knew what an electron was. So, with the benefit of hindsight, you go back and you look at, I mean, they thought there was an ether that radio waves propagated through. And that's not the way we think nowadays. But when you just think about electrons interacting with other electrons, that's really what it's about. Then would we really write down the same equations today that Maxwell and Heaviside and Hertz wrote down? And it's my contention that you wouldn't. A much simpler way to view all electrical things.
Let me interrupt you just. Now, Maxwell's equations, of course, are so foundational to our understanding and thinking.
They have been treated as though they were foundational. They're actually a very clumsy set of equations to work with, and the reason is because they're expressing relationships that would apply if we had an ether. And if one thinks instead about one electron interacting with another electron and massive numbers of them interacting, then you wouldn't start where that started. And the simplest thing to start with is this thing we call a superconductor. And the reason why that's the simplest is that it doesn't have any of the complications of losses. There's no thermodynamics in it once it's a superconductor. There's thermodynamics in it to get there. But once you have the superconductor, it's an extremely simple to understand object. And the relationships that you get from it are extremely simple. And I've tried to lay out a short version of that in my little green book. But
collective electrodynamics.
yeah, well, that was I probably shouldn't have given it that name because it frightens everybody. But and when I say superconductor, it frightens everybody.
Right.
And it's true that trying to figure out why and at what temperature a substance becomes a superconductor is a very hard thing and has not been figured out to this day. After all these years, there's a formulation that describes a small subset of superconductors that gives us a partial understanding. That was Bardeen and his collaborators that figured that out. But it doesn't give the whole picture. So there's still mysteries there.
9 Nobel Prizes, though.
Yeah. Well, and rightly so. Those steps were big ones, but we still have a lot to learn there. But once you have a superconductor, you don't need Maxwell's equations.
Right.
They're just treating the electron as a wave the electrons in the superconductor all lock into phase. That's why it's superconducting. And once you know that, you can write down what they do simply. So that was the quest that I've been on since then.
But is that the difference between theory and practical? Because Maxwell's equations are kind of where we live, right?
Well, it was a complicated way to express a simple thing once you understand that it's simple.
Mm-hmm.
It went through itself several versions. Maxwell wrote 20 equations down that are very hard to reason with. And then Heaviside came along and simplified that down to 4 equations, which still had an ether in it. Mm-hmm. And you can do much simpler and develop much more intuition by working with the simpler formulation that involves electrons interacting with other electrons directly. And that turns out to be something that once you get it, a whole bunch of things become obvious that weren't obvious before. Mm-hmm. But academia is not open to new ideas without big struggles, in the same way that nobody would believe you could do Moore's law. They don't believe you can do a simple version of electromagnetic stuff.
It really made a lot of difference to me. Carver told me years ago that electrons in the atom are superconducting. That's why they don't plunge into the nucleus. Yeah. And that's a pretty simple, if there's no interference, superconductivity is the natural intrinsic condition of matter. And that seemed really simple to me. I probably am oversimplifying it now, but this is the kind of vision that Carver gave me throughout my career that made it possible for me to write about these complex matters.
So how do we relate this to the quantum world?
Once it's in a superconducting state, it behaves just like a radio wave or any other wave. Mm-hmm. There's details, of course, about how it got there. But once it's in a coherent state where there's a bunch of electrons sharing this wave function, it's just like any other wave. And you can reason about it the way we engineers reason about waves all the time. We live and breathe the waves in electrical engineering. And so people that, and engineers are, by nature, have an intuitive grasp of what they're working with. Mm-hmm. And the equations come later. But if you're going to invent something, you can't invent things with equations. You invent things because of physical phenomena that you understand and you can visualize. And then once you've figured out what kind of thing it is that's possible, then you sit down and analyze it, and it takes a little math to do that. Mm-hmm. But you don't start that way.
Okay.
So all this stuff that you hear about, our new great science has created the modern world. No, engineers created the modern world. And they had to learn a little analysis to do it, but mostly they had physical pictures and they went in the lab and worked them out and got experiments to work. And that's what built the modern world.
Quantum tunneling was where you started, right? Wasn't that almost?
Yeah. And the physicists have known about that since the early days of quantum mechanics. Mm. But when I was taking courses from those guys, the only example they used was a nuclear decay. Mm. Well, I mean, that's nice to know that, but actually the nuclei decay and you can't calculate how they're going to decay. To this day, you can't. So you go measure it. And that's what the modern world was built on. If you can't calculate something that's too hard, you go measure it. And that's how the nuclear reactors were created and all of that. Not by heavy-duty fancy theory. It was very straightforward theory. So,
Okay. What are your thoughts on the state of quantum computing?
I've been very supportive of efforts to do quantum computing for a different reason than everybody else is. What it has caused to happen is a whole bunch of math that predicts a whole bunch of things. And then some people really going in the lab and trying to build quantum computers. And in order to do that, you have to get a real handle on hands-on quantum mechanics. You have to get down there and do real experiments with quantum systems. And the experimental part of that has been going very nicely. People are learning how to actually, how do I interface with the quantum world? I mentioned superconductivity. That's in a way, it's the earliest real interaction that we could control and figure things out. The discovery of superconductivity, this thing has zero resistance. Well, how do you prove it's zero resistance? Well, you make a ring of wire and get a current flowing in it, and you can snoop on it with a little magnet, and you don't ruin it. So you can test it without messing it up. So here you have a quantum system that's lossless, has to be a quantum system if it's going to be lossless for the reason you said. And by the way, what George said is right, that an electron in an orbit around an atom, that orbit is a superconductor. Exactly the same thing happens in a ring of superconducting wire. You get a current flowing in it, it just keeps flowing. So that experiment was really the beginning of hands-on quantum mechanics. And now they're doing wonderful experiments.
Yeah.
Whether the theory will work out or not, who knows? Whether we will get quantum computers or not, who knows? One of the things that I believe without proof is that anything that ends up being a quantum computer will look quite differently than anything we've seen to date. It's going to take a lot of invention, and that invention is going to require real hands-on familiarity with quantum systems. And we don't have. The way kids get taught quantum mechanics is Neanderthal. It's just ridiculous. They're taught it as, oh, here's this equation. You do things this way, you do this kind of math, and you follow these rules, and that's quantum mechanics. And that's not the way you approach a thing if you want to use it and work with it and have it create new technology for you. It just doesn't work that way.
So how do you see your work in this area informing progress and work in the area of quantum computers?
I don't see it right now.
Okay.
I don't see anything that I've understood helping what they today call quantum computing.
Okay.
They're using this mathematical model that you think is too complex and possibly unreal. Isn't that, or
Well,
is that not true?
I don't know if I would call it unreal. They've developed a very fancy mathematics that keeps getting more and more fancy. And the concepts that are being used today may or may not be the concepts that would make a tighter connection between the quantum nature of matter and information processing. So when you say quantum computer, what you mean is there are a whole bunch of phenomena that are essential quantum phenomena. The wave nature of matter is basically what defines quantum systems. Quantum mechanics is not a picture of quantum systems, it's a mathematical recipe. It's basically an algorithm. You just follow these rules and you'll get a solution to this. Makes lots of assumptions and doesn't comprehend a lot of real world things you would do if you were going to move forward. That's getting better because people are doing real experiments.
Okay.
So that's why it's such an important thing for people to be doing, is so we can get more hands-on. Sooner or later, they'll have to start teaching students from the intuitive point of view how these things work. And not just teaching them math. You can go through a whole course of study in physics and never actually do a quantum experiment yourself. That's not the way to have an engineering outcome. But now what's going to happen? I don't know what's going to happen.
Carver, you were there teaching a course with Feynman when he gave the great speech that called for quantum computing and really envisaged the universe as a quantum computer.
You could call it that.
Yeah.
But what we mean by a computer, I had a lot of discussions with Dick about this because I was interested in building computers and the technology with which you do that. He was deeply interested in the fundamental things behind that. And so we had lots of arguments, and it was good.
They taught the course on the physics of computation.
Which was great fun.
Which was really the first course that defined this whole field, the physics of computation, that these were two separate domains, and Carver and Feynman and Hopfield, I guess,
absolutely
integrated these three fields.
I want to go back to your collaboration with Feynman on developing this course on the physics of computation. How would you characterize that, physics of computation?
We all had very different backgrounds, which was great. And we all had this notion that that our idea of a computer was extremely limited. That's the whole concept had shrunk down upon the things we knew how to do at the time. And that was in many dimensions. And we all felt like there's got to be ways of processing information that are much richer than just NAND gates and NOR gates and stored programs one step at a time computing. And what each of us meant by that was very different because of our backgrounds. So Hopfield was off for the spin glasses because that was an outstanding problem in physics, and he was able to work it. Real major thing. And I was busy building things. So, you know, we had this great substrate that we were starting to make bigger and bigger wafers with more and more transistors. And the last big step in electronics had been Noyce and Kilby figuring out that you could just take transistors there and hook them up right
Hook
where
'em
they
up,
are,
right.
and not have to cut them all up and then hook them all together again. And that was a key step. Well,
Right.
Once you have that many transistors all together, we know of an information processing system that does that, you know, neural tissue does that. Highly interconnected, more local connections than distant connections, all the things you'd think about. We could do that on silicon. So why don't we see what we could do? So that was my approach, having gone through the Moore's Law thing. And then Dick, of course, was
Feynman.
he was deep into the quantum systems and had his own ideas about all that. You couldn't imagine three people with more different backgrounds looking at this problem of we must be missing something important, because doing a one step at a time thing with NAND gates and NOR gates and memory.
Yeah, the whole von Neumann
Yeah,
thing.
that we were by then so deep into that nobody could see anything else. Anything else was an algorithm, you know. And so
Yeah, it's true.
that's how we got together. Oh, it was sort of they often say that faculty are a group that's held together by a common complaint over parking.
Okay, there you go.
And we were a group held together by a common complaint over computation.
Yeah.
So that's how we got together.
I want to come back to silicon. As you've noticed, observed, silicon isn't a particularly great semiconductor. There are better ones.
Yeah, a lot better
You know,
ones.
I mean,
yeah.
gallium arsenide, for example,
Yeah.
where you have a lot of
Yeah.
work,
Yeah.
innovation.
Yeah.
Yeah, and yet you see it remaining a workhorse for some time.
You know, I had a lot of those discussions with Gordon.
Okay.
And Gordon once, when we were having this discussion in the early morning, he said, "Carver, it isn't really a silicon technology. It's a silicon oxide technology."
Okay.
Yeah.
Yeah.
Gordon got his degree in chemistry
He was
with
a
a
chemist.
minor in physics. So he was, you know, he could see that. And anytime you make something, well, processing silicon wafer is, I think it's fair to say it's the most exacting chemical process that's ever been developed.
Yeah, I believe it.
You may come up with a better one, but I don't know of anything. And so in order to do that kind of chemistry, I learned, you know, in my work with semiconductor materials, I did dozens of them. And some of them were just magical when you went to build electronic structures, and others just wouldn't cooperate. And that was all about chemistry. And if you get the chemistry right, then you can start doing the physics. But if you don't get the chemistry right, nothing will help you. So Gordon was right
I
on.
understood that.
Gordon had this great sort of view that it was almost providential that silicon, aluminum, and oxygen would be the elements that we choose for our major information technology, because they are the most abundant elements on
That's
the
true.
face of the earth. And so we chose the three most abundant elements on the face of the earth for our substrate and processing: aluminum,
Yeah.
oxygen, and silicon.
What do you think of graphene?
I think it's a wonderful material.
Does it have a future potentially to displace?
This is a bigoted view, so I'll give you a bigoted view. I think saying that we want to replace silicon is a misplaced goal. I think silicon will be here from now on. Are there things that have a potential to do something different that is remarkable? Oh, there are a lot of those things. Most of them we haven't identified yet. Is graphene going to be one of them? It's rare that you can answer questions like that ahead of time. What particular material will have the particular properties that allows it to turn into a major industry? And of course, what's happened in silicon is that a lot of other materials have been brought in as we got past our 0.1 micron. And that now you start running into all the problems we identified. And of course, you can make progress, but it's harder and harder going. You wouldn't have got here if we hadn't had the silicon sort of by itself have all the properties you needed.
Correct.
And then, you know, from that, you can introduce other things, and that's tough going. I mean, the introduction of these other materials has been a major challenge, still is. As late as 1931, I was reading a paper just the other day by the people who really worked out the semiconductor physics stuff. And they said, well, you know, materials are really different. Silicon seems to be a metal, and then there are things like selenium that are semiconductors, and then germanium may be able to go back and forth from one to the other. And now those are the people that gave us the picture that the Shockley-Bardeen group worked with to get their first active semiconductor device.
On germanium.
Yeah, and it turned out they had figured out how to get better silicon, but it was so hard to work with that they did work with germanium.
I just want to give one other angle to the graphene question. I mean, graphene rolled up produces carbon nanotubes.
Right.
And there are lots of uses for carbon nanotubes, including possibly new dynamic, non-volatile memory. And that is, you know, that may be introduced this year. At least Fujitsu and Nantero together have announced that they're going to produce in volume carbon nanotube-based memory. But they've been announcing such things for a long time, I have to say, and that confirms Carver's skepticism. And I think this is important moment, though.
Is by the same token. So we're at 7 nanometers now, state-of-the-art fab. Okay, we don't have a whole lot of headroom before we start running into, again, a whole new raft of serious physics problems.
Well,
are we going to stabilize here?
Oh, I would never. The size of the elementary geometry in an integrated process is not the only variable.
Well, that's true.
And there are a lot of ways to add value other than just shrinking. So what happened is, once we were able to show that nothing bad happens till you get 3 orders of magnitude, or it's 4 orders of magnitude below where we were when we made that prediction. Then people found out that if you just went forward and shrunk it, you'd beat the people out that were trying to do fancier things.
Mm-hmm.
And that got built into the industry to the point where it didn't have any people that even knew where it came from. Because people retired that had done some of the early physics. And then you ended up with this technology, and all you had to do is shrink it. So that got to be a mindset. And it worked, because that was a short term. It only took one step.
Got a lot of mileage out of that.
Yeah, and it went for a long time. And so we lost out of the industry the people that were thinking about longer term things.
Yeah.
And
The other variables.
yeah. So now, where's that going to come from? We don't know.
Okay.
Because it's not on anybody's roadmap, or if it is, it's the very short-term things. So what I think will happen is that somebody somewhere will have the tenacity to get a totally new architecture, like, for example, the neural systems that just work on a different principle than any information processing thing we have made, including deep learning. It has very little of the organization of neuromorphic systems. It's just an algorithm.
That's true.
And nobody has really built much of a system using the principles that the brains of animals use. And in fact, only a few of those are known. I've mentioned some of them, but there's a whole lot going on that we don't even know.
This is why I think neuromorphic technology is ultimately going to gravitate back to carbon. That's what our neuromorphic systems use. And I think ultimately we're going to things like graphene and carbon nanotubes are precursors to a new carbon economy of information. And I've been interested in big numbers for a long time, and I got intrigued with zettabytes when it was, when we were projecting how big the World Wide Web could get. And finally it's into zettabytes. And a few weeks ago I learned that, so the whole World Wide Web is a zettabyte or several zettabytes of information, while the connectome of one human brain, I learned, takes a zettabyte to map. And the one human brain works in watts, 10 to 12 watts.
Tiny, yeah.
And the zettabyte on the internet works in gigawatts.
Yeah.
And there's just no comparison.
Right.
And the idea that, this is a different challenge which Carver opened up in his laboratory with his neuromorphic vision. And I think we're ultimately going to have to keep returning to Carver's insight in the future. And it will manifest itself in carbon artificial intelligence.
So will we ever transcend the notion of a transistor?
I think we will always have transistors in the same sense that you can still buy hammers and saws. They haven't gone away.
No.
They've been around for centuries. Each one was a major step when it was invented. You know, there was technology before the Industrial Revolution.
Mm-hmm.
And so, you know, there are certain kinds of things that do the job that they're doing as well as it needs to be done.
They just work.
And it's all debugged and it's all way down the learning curve. And to try to break into that, you have to do something that's of enough value to change a whole technology to do it. And that takes vastly longer than a new technology for a urgent felt need that you can't do with the old.
So you were also one of the very first to suggest the possibility of integrating millions of transistors on a single chip, okay? Which led you to investigate techniques for very large-scale integration, VLSI, designing and creating high-complexity microchips. This was a big idea.
Our part of that, we weren't the people that invented that idea. It was really Gordon and his vision that brought that idea to the fore. Our part of that was to realize that you were never going to get there if you couldn't translate the functional description into a physical description.
In other words, how in the world are we going to design these circuits
Yeah.
with millions of transistors?
Yeah, never been done.
Right.
No one had ever made anything with millions of moving parts and made it work.
Right.
And so we had to change the way we were going to do that. So that was the part we took on. And, you know, after the scaling, it became obvious that that was going to be the problem.
That's the
Now-
next challenge.
Yeah, once you got a technology that would do that, and there was a lot of economic incentive, as Gordon kept pointing out, to do that, it was going to happen. It had already started happening. And so, okay, now, if you're really going to keep doing that, you have to be able to design it and have some idea if it's going to work and that sort of thing. And that turned out to be a fun,
Yeah.
because it was not a difficult concept, but it went against the grain of all the way everybody was doing things. So that was another.
Again.
Yeah, I felt familiar.
Yeah. So what is it that gave Gordon Moore the idea that lots of transistors on a chip would be important, especially considering that at that time we were still a long ways off from thoughts of VLSI or the kinds of applications that would make that matter? What were those conversations like then?
Gordon is an astute observer of what is happening. So his plot being my, Exhibit A of whenever Gordon sees something, he thinks very deeply about what is happening. And that's an example. And it's a particular way of thinking that gets you to do what Gordon did. And then, of course, once he points it out in a very clear manner, then all of us had the idea because it's so obvious.
Exactly, especially in hindsight.
Well, yeah, it was hindsight for all of us once Gordon told us,
Yeah.
you know. So Gordon just thinks about things in that very deep, very I think he thinks about things like that, like I think about engineering or physics problems. You know, there's a way of thinking that works with each kind of phenomenon, and he just really is good at that. Those are interesting questions, because I would stop by in my morning of the consulting day, and what should I be looking at? And he went, well, why don't you look into this? And there's some guys over here that are doing that. Why don't you figure out what they're doing? And so then I would come back, and we'd often go off to dinner, go pick up Betty, and we'd go down to the local restaurant and have dinner. And what's and so it was like George that way, that when people talk to him about things, he puts it together on a bigger scale. And George is phenomenal at that.
Didn't you tell Gordon about tunneling and tunneling phenomena, which were really the root of the whole Moore's law projection?
That was the question, right?
Well, see, Gordon didn't make the projection from any physical thing. Yeah. Gordon made the projection from observing what is happening. Yeah. Yeah. And he saw this thing going over quite a range, and he said, exponentials are interesting. By observing the phenomenon. And we had talks about tunneling and stuff, but the thought that would limit the size of transistors, I mean, he was orders of magnitude ahead of that, but thinking way out there. So you talk about, short-term and long-term. Right. Gordon is a very long-term guy.
Well,
I mean, astoundingly so.
Another huge multiplier effect was the idea of the multi-project wafer, or the shared wafers, because that meant now that even students could design and have their chips made. So you had a role to play in all this.
Yeah, well, we sort of put that together in our homespun way because of the course here at Caltech, because I started teaching the VLSI design course in 1971.
And with your clock chip.
Yeah, yeah. And the students just wanted to learn about it, so I'll teach a course in it. And so we had to get fabs somehow. So we had a couple of former students who were in the fabs at Intel. And so, I would get the masks made, because you could go to a commercial mask making house. I learned how to write Gerber code so we could make the masks automatically, so you weren't. Intel was still cutting Rubylith.
Yeah, Rubylith, right.
I know, it's unbelievable. And so we just had to find a way that we could all keep learning, and that meant we had to get fabbed. And so after Ted Jenkins, he's a Caltech trustee right now, a great guy. And he was a former student that went to work at Intel, and he was in charge of the fab over in Livermore. And so I would get the masks made and take them to Ted, and take Ted and his collaborator there to dinner, and we'd talk about stuff. And then when I saw Gordon and Bob the following week, I said, I just wanted to tell you that I'm sneaking a run through your fab.
Little shuttle.
And Bob looked at Gordon. He looked at me.
Bob Noyce.
Yes.
Yeah. And he looked at me and he said, I think we'd rather not know about that.
Really?
Yeah. So that was our first foundry. And the word foundry was not my invention. I was having dinner with Gordon one night and asking him about this new fab they were putting up in Livermore. And he said, yeah, that's a foundry for stamping out 1103s. So his idea of a dedicated fab that just stamped things out was, he thought that was a foundry. So
That's funny.
Gordon is the one that invented the term
son
silicon
of a gun.
foundry. They weren't one for anybody else, but they were for themselves. So,
Oh, that's funny.
and if you think about it, the innovation there is, if you've been on both sides of the fab and the physics and the design, you realize that the amount of information you have to pass across that boundary from the layout to the fab is tiny. You have a set of design rules, and then you just pass over the geometry. That's it.
Run it through the process.
Yeah. So it's basically, they hated me when I said this, but it's basically color printing
Sure.
in terms of the information you need. You just need the color separation. Now, you need to know quite a lot to do that, so you have to have design rules. And you have to have figured out the circuit and the system and how that was all going to work. None of that involves chemistry. The fab is all about chemistry. So there's a place to pass information across, which the people on opposite sides of that don't speak the same language, except that narrow little thing.
That interface of the mask set.
Yeah, you interface at the level of the mask, and the designer has to know the design rules. So that's it. Anytime there's that kind of thing, it's like printing. You don't care what book you're printing. And the writer of the book doesn't care who prints it, as long as they do a good job. And it turned out, when I first started preaching that little sermon, both sides were so angry at me they couldn't see straight.
And what were they angry about? They were angry.
Well, I was complaining to a friend of mine at dinner one night about this, and he said, Carver, it's a Protestant rite in a Catholic church. See, I was doing this, gathering up the student projects and making a Gerber deck that put them together myself.
Yeah.
Well, that was fine for my little class and my research group. And of course, after you've shown them how, then the students get better than you are at doing stuff. That's just the way it works. If they aren't, you're not doing your job as a professor. But when we started getting other universities started, teaching the course, and they wanted to get fab.
Sure.
And so then Ivan Sutherland had this idea that we should make a place that would do that, gather up the projects from all around the different universities and batch them up on a wafer, just like we were doing for the single class. And so there's a former student by the name of George Lewicki who was working up at JPL. And so he had kind of followed what was, he hadn't been in on the VLSI part, but smart guy, and he had worked on some of the tunneling stuff.
Okay.
And so I knew him really well, and he very energetic and smart guy. And so I introduced him to Ivan, and we were all talking about, could we get JPL set up to do this? Because they could get government funding for it, and they knew how to do project management like nobody else.
Right.
And wouldn't they be ideal? And we were all convinced that was going to work. But as it turned out, JPL had gotten a lot bigger, and this isn't what they did. And it didn't work. So I even knew some people over at ISI, which is a lab that's attached to USC. And they're over in Marina del Rey. And he had some former students there. We got them to approach DARPA, and they made a deal that DARPA would jumpstart this thing.
Oh.
And they didn't have anybody that knew enough, so George Lewicki went over there from JPL and started Moses. And then they still going.
Yeah.
And doing, as near as I can see, a good job of.
I was submitting shared wafer projects back in the early 80s to Moses and through micron gate arrays. It's incredible. Yeah.
Yeah, and they're still going.
It's still going.
So it was a really good thing.
And you'd get your 10 parts back. And
Yeah, yeah. It's got a lot of students to where they could just go out in the industry and design things.
yeah, and you could try things. And this is really, it became incredibly important because it just sparked a massive torrent of innovation simply because people could actually try things.
Yeah, oh yeah. It's what I
Hugely
was saying
consequential.
about the difference between the theory and the practice.
Yeah,
If you don't let them actually do one and get it working, they don't know what they're talking about. And if they've done that, nobody can stop them.
Yeah.
right. And it opens up just all kinds of possibilities, which leads us to kind of a philosophy of possibility, if you will. To get there, and again, sort of closing the loop again with Moore's law, you said, I always had to explain that Moore's law is not a law of physics. This is a law of the way that humans are. In order for anything to evolve like our semiconductor technology has evolved, it takes an enormous amount of creative effort by a large number of smart people. They have to believe that the effort is going to result in a successful thing, or they won't put the effort in. The belief that it's possible to do this thing is what causes the thing to happen. Yeah.
You have to have two things. You have to have a belief that it's possible, and you have to have the belief that if you do it, it'll make a big difference.
Another expression of Moore's law is you say it allowed people to believe. They gave them a mechanism
Yes.
Yeah.
to work
Yes.
on.
It by the time it became Moore's law, we had gotten past the major obstacles to belief. And Gordon had made this absolutely compelling case that if you could do it, it would transform the industry. There was no question about that. But there are a lot of questions about, could you do it?
Right.
So that's what we had to get past. Gordon was very successful in getting people to believe that it was worth doing.
Yeah.
He got there before we did.
And George, you would agree the essential thesis that technology progress is not inevitable.
No, it's not inevitable. Progress entails intelligent design.
A creative motive
Yep,
force behind it.
creativity,
Yeah.
which always comes as a surprise to us. Creativity comes as a surprise. If it didn't, we wouldn't need it. And planning would work. We could plan everything. And
Exactly.
the whole future would lie before us. But creativity is surprising.
Well, it's like you say, if you already know the contents of a message, then it contains zero surprise and therefore zero information, right? Information in your context is this unexpected
Yeah, unexpected
content.
bits.
It's this, to continue your thought, it's this disequilibrium and disorder, not order. An orderly and predictable mechanism, a great machine, as you say, embodies no new information.
Yeah, and we see in the world that the societies that get centrally controlled have just they don't explore enough space to find the surprising things, because you get such a small group of people making all the decisions. And so you don't get surprise, and you don't get progress, and you don't get a working economy, and you don't get prosperity.
It stagnates.
Yeah, yeah. Not just stagnant, it retrogresses.
Something else you said that impressed me was, mimicking physics, economists seek determinism and thus erroneously banish surprise and creativity.
Yep.
Retrograde.
And we've seen many cultures do that experiment.
Yeah.
We try to guarantee progress, but a learning process can't be guaranteed because it's finding out things we don't already know. So a government guarantee or effort to force progress actually thwarts learning and thus thwarts economic growth and creation.
So I want to get to a particular paradox of information theory, which effectively began with Kurt Gödel's demonstration in 1930 that all logical systems, including mathematics, depend on axioms that they cannot prove. Okay? Mathematics, and hence all mathematically based sciences, from physics and chemistry to biology and economics, ultimately rests on a foundation of faith.
Mm-hmm. That description is the basis on which I work every day. Let me put my scientist hat on.
Yeah.
If a scientist doesn't believe there's a rational universe that one can apprehend in some sense, we couldn't be scientists. No way. Actually, Einstein was asked that question, and that was basically the answer he gave. That plays directly to what we were just talking about, that if you think it's a closed system and you can just go and work it all out, and you're smart and you can just make everything come out the best it could. Totally flawed belief. It shows up in science. Science is rife with it now. They teach students all about the big breakthroughs in science, and they get to here, and basically they then say, and now we know it all.
Settled science.
Yeah. Why did anybody think it's any different than it's ever been? Mm-hmm. It's not a closed system. Yeah. But our faculties teach courses as if they were rote, as if this is the end of it, and all you do is you learn that, and now you know what to do, and you go out and... It isn't like that. It's like what you just read. Mm-hmm. And that's a huge problem with our educational system.
Well, it's also sort of a fundamental problem of experts, right? Mm-hmm. I mean, they are at a distinct disadvantage when it comes to unbridled creativity and imagining radical possibilities, right? Mm-hmm. He simply knows too much, right?
Well, they know too, as they say, more and more about less and less.
Exactly. So my question for you is how you get past the handicap of being an expert in so many fields, and how and when do you know to attempt something because you don't know that it can't be done?
Because he's master in so many fields. He doesn't narrow his focus. He doesn't know more and more about less and less. All his career has been sort of Newtonian ocean opening up horizons before him, where he learns as he learns, the horizons of ignorance grow greater, and thus the opportunities for creativity become higher.
Personally, I have never felt that I was an expert in a field. Because to me, there was always things that it was very clear I didn't understand. And it looked to me like other people didn't really understand them either. But who am I to, these people are spouting all this stuff and they're acting like they understand it all.
Right.
This may be a hyperbole, but it's a reality of really wise explorers. They understand that the more they explore, the smaller proportion of the total universe of knowledge they command.
Mm-hmm.
Yeah. It's a really bad disease that our society, our educational institutions and all, act as though there's this finite amount of stuff that you have to master,
mm-hmm.
and then you are one. And it just isn't like that. And it's maddening if you're in a field, because people all around you are, if you're asking questions beyond the way it's thought of, they say, oh, you just don't get it.
Right.
And it's true. It's a true statement, but for a different reason. Anytime you treat a thing as if it's a closed system, then there's an indefinite amount of stuff outside the boundary of that thing, and you're pretending it isn't there.
Yeah.
And if someone's interested in what's out there, they're derided by people in the field because it doesn't fit in. So they say, oh, it's not in this field. Okay.
You write about this, John, the economy of abundance. If you focus on the scarcities, you end up in a zero-sum game and a zero-sum economy and a struggle for power rather than a search for knowledge.
Right. Exactly. Well, this is why I think it's interesting in this context, something you said, Carver. It happened with every company I've worked with. They get to the point of where they're successful, they're on a track, and then there's less and less that someone like me can contribute. You actually become a distraction. They're trying to focus, and you're wandering around thinking about all these interesting new questions, and that's when it's time for me to leave.
Yeah. But let me add to that it's absolutely essential that a young company focus on one thing they can get to market and get it accepted and get profitable.
Mm-hmm.
And if they don't, they're going to go belly up. So I wasn't criticizing.
Right.
It's essential.
How many companies? Carver's been involved in starting 20 companies at least, isn't it? Or is it more than that by now?
Closer to 30, but yeah.
It's closer to 30.
Mm-hmm.
And we've had lots of different outcomes, but getting that first product and getting it accepted and getting it profitable and, to be ahead of all the competition and all that, that's essential.
Absolutely. But it's your ever curious nature that can get in the way of that when you're involved in.
It's not what I do.
Yeah, that's not your role there.
It's not what I do.
You know when it's time to step out.
Yeah.
And go on to the next one.
Yeah. And
and change fields again.
Yeah. It's not any criticism of the nature of startups and how creativity works in business.
Right.
Because what they're doing is a step towards a very creative thing.
Yes.
And that step has to work. Just like in an experimental science thing, if you can't make that experiment work, there's no next experiment.
Exactly right.
This is really the rule of learning. You have to state a falsifiable hypothesis.
Yes.
It has to be able to go bankrupt. It has to have
exactly.
Yeah, falsifiable meaning that it can fail.
Yeah, being disproven, in that case being going belly up.
Mm-hmm. Well, and that could just be a function of bad execution, right?
It could be.
Or it could be that it isn't the right thing at the right time.
There's that too.
Yeah.
And that,
That's what you learn.
And what you don't want is the government coming in and bailing out things that are too important.
Too big to be falsified.
Yeah, because once you're in that position, that becomes a problem rather than an opportunity.
Yeah. And this really is systemic in many aspects of academia, certainly in education. You're fond of quoting Robert A. Heinlein, who wrote, I'll read this, "Throughout history, poverty is the normal condition of man. Advances which permit this norm to be exceeded here and there, now and then, are the work of an extremely small minority, frequently despised, often condemned, and almost always opposed by all right-thinking people. Whenever this tiny minority is kept from creating, or, as sometimes happens, is driven out of a society, the people then slip back into abject poverty. This is known as..."
Bad luck, yes.
Yeah.
That Heinlein had a lot of very good insights. That's my favorite.
Yes.
And that was really what we've been talking about.
It is. So the question is, how do we turn this small minority into something that might approximate, a critical mass? I mean, how do we cultivate more thinking along the lines of this otherwise extremely small minority? Right?
Well, let's start with our educational system.
Let's start with the educational system.
You don't teach kids that here is this thing you have to understand and then you'll be one. That it's a closed system and everything's known.
Mm-hmm.
There's nothing that will turn off a curious kid more than telling them that.
Yeah.
You just make sure you can do all this fancy math and do all of these things, and you'll be in grad school, and then you'll be able to do something, maybe. No.
No. I mean,
Kids can go out at any age and come up with something really creative. It may not be that in its first incarnation it will change the world, but if they keep on it, they'll learn their way through it. But they don't do it by telling them, well, go memorize all this stuff that we know already.
right.
That's not how you go at it.
Well, face it. I mean, education system is famous for literally beating the creative imagination out of students.
Absolutely.
Right? And this has actually been well studied, for example, by Land and Jarman. Some landmark studies that they did where they looked at very young students and they tested at the genius level in creativity. Okay, by the time they finished high school, they were performing pretty poorly. Okay, what was the intervening event? Education.
Yes.
Right? Yeah. So, how do we fix that? How do we teach creativity? How do we cultivate a sense of curiosity? How do we stimulate imagination in students? This would be a significant paradigm shift in the way our education system works.
The only way I know how to do that is just to expose young people to opportunity to learn. And the ones that get it about a certain thing will follow that. And that's why I hate the idea of required courses. It's a horrible idea because you're going to, the net result is going to be they never want to see that subject again for a lot of students.
It's true.
Don't do that. Kids are born with the innate curiosity.
Yeah.
And our system beats it out of them. And why do you do that? Why would you do that? Good teachers know how to make things interesting and not to force kids in things that they can't stand. And we're stuck, badly stuck in our education system. And as you know, from an economic perspective, I went to a one-room schoolhouse.
Yes, it was just fascinating.
I did too.
Yeah.
Did you really?
Yeah.
Yeah.
And the great thing is you get to listen in on the stuff that they're learning, whatever's interesting. So you built in ADD, right?
Yeah.
So,
Which is actually a very healthy thing.
it's the only way you're going to get students to find a thing they're fascinated by. And
Exactly.
And if you don't let them do that, get back and learn what you're supposed to be learning. Maybe I'm not interested in what I'm supposed to be learning. So you teach me how to hate it worse than I hated it going in.
Right.
Then you get the outcome that you mentioned.
Right.
Don't do that.
Don't do that. Well, it's interesting. I mean, you said that you struggled as a student for a very interesting reason. You said, I came here to Caltech because I really wanted to understand this stuff. And that's much harder than just learning how to do things.
Yeah, yeah. And in the early years, all we did was kind of boot camp. You go get good at this. It isn't interesting? Okay, you flunk. Well, fortunately, I was able to get into courses that I was interested in.
Yeah,
And I had some good teachers.
you did.
And then it was fun, and I learned a lot, and I had a lot of open questions that I would go ask to teachers about. And if it hadn't been for that, I did not do well in the first 2 years because it was this pro forma education stuff. Yeah.
Yeah. And along the way, you figured out the best way to learn something is also just to teach it.
Oh yeah. Oh yeah. Everybody learns that.
Yeah, you do.
Even people who are not teachers for a living. I knew some people that were, good in other areas, in industry and other places, and I learned a lot from them. So that was, the best of teaching. And I've tried to do that for young people that I've known.
Why homeschooling is so effective, not just for the kids, but for the teacher parents. You really learn a lot trying to teach your kids physics and math and English and all the key disciplines, history.
In the context of curiosity and imagination and learning, I'm also very interested in the design of experiments. And in history, we've had some amazing experimenters. Of course, Faraday, Michelson-Morley, the famously failed experiment of attempting to measure the speed of light in ether.
Yeah, in ether.
But yet that went on to actually inspire Einstein. So it was a failure for these poor guys, but it did have its payoff later. So how do you approach this design of experiments? How do you look at a problem and sort it out?
For me, that phrase is an oxymoron. I have never designed an experiment. I just go do them. And you muck around with it for a while and you get a feeling for what the thing wants to do. It's usually very different than you thought going in. You have an idea, so instead of designing it, you muck around with it and oh, I didn't think of that. So what's that about? Some of those things will be things people know already. And then you get to one and you look around and it doesn't seem like anybody knows about it. And so to me, experiments evolve. They don't, you don't design one. You go explore and you do the simplest things to try to figure out what's going on. And then it starts, often in a very rough way, it starts speaking to you. You start to, this experiment's trying to teach me something and I'm not listening very well. And you get that. And then you land on say, oh, that worked. So then you start going down and then Oh, well, that must be X. So you try X. Oh, that didn't work. What's going on? I did this because it was obvious from the last one that it should work, and it doesn't work. Now, and then you muck around with that for a while, and then all of a sudden you see, oh, how dumb. I'm so stupid. You remember.
Listen to the technology. Find out what it's trying to tell you is what one of the first things Carver told me.
Yes.
Yeah, and in my research group, we had a group meeting once a week, and we'd had it at dinner time, and we'd bring in food because there's nothing that students are more interested, well, only a few things are more interested in food. And the first thing we always did is a thing we called confession, because it was absolutely required that if you had done an experiment and it didn't work, that you would share it with other people. And that's why it was called confession. Because normally people don't want to talk about things that don't work.
No.
But actually, that's when you learn.
Yeah.
That's what George was saying. If it's a thing that doesn't fit, that's information.
Right.
If it does what you thought, you haven't learned anything.
Yep.
So
Exactly.
you're absolutely bound. If you're going to be in this group, when you get something that doesn't work, you share it. Mm-hmm. Whether you figured it out or not. And if you figured it out, you can share what the solution was. And if you haven't figured it out, very often somebody will say, well, could it be blah, blah, blah? And that might get you on a track that'll solve it. But there's always information there.
Yeah. Well, it's like Edison said, right? We now know 999 ways that a light bulb will not work.
Yes.
So really, I mean, you're more of an improviser. You're more of a jazz musician than a classical musician in that sense.
He's a classical composer.
Classical composer, right, exactly.
I don't know any.
That's the axiom outside that produces the system.
Yeah, that's very interesting.
Turing's oracle, you know.
Yeah.
He said any computer technology is dependent on a programmer, an oracle that's outside the system. It was Turing's translation of Gödel's incompleteness.
Yes.
Uh-huh.
The axiom outside, the person outside, the oracle.
Yeah.
And that was, that's how I thought of Carver. And the entrepreneur. I think the oracle that launches the system is the best model of the entrepreneur. It's why these small companies at some point have to focus.
Right.
They've created their coherent system, and at that point, the oracle has already played his role. And
It's very interesting. There was a study done quite a while back where they compared companies that started with a well-defined product and a well-defined business plan and had worked it all out ahead of time, and companies that had a technology and launched a business to find a way to create value with that technology. And everybody thought that it was going to show absolutely that the company that were well prepared and had studied the market and all that were going to always. But it turns out that the second kind of company that has a technology looking for an application, vastly more likely to be successful. Because if you could do the other thing, the incumbent's already done it.
yeah.
And they're going to be there before you are. And a startup has no chance in that situation.
Right.
And of course, I've always felt like I was a newcomer in anything I was doing because I hadn't studied it, had no classes in anything I've ever done. And you know, so there's no hope if you walk into a field where everybody knows how to do it. You just get slaughtered, that's
Right.
all. Yeah. So if you're going to do something really new, you know, you got to be out there where nobody else is.
Right. And one of your sources of inspiration is nature, you know, like biomimicry.
Yeah.
So I'd like to explore this with you a bit. Case in point, back in the 80s, while AI was still very much in the realm of theory, you were actually developing this concept of neuromorphic computing.
Well, it wasn't that AI was just theory. They were building algorithms with it. But those were algorithms for ordinary von Neumann computers, one step at a time. And I was looking for a way to make it that it flowed the way information flows in the real world. Mm-hmm. That it isn't one step at a time, and it's everything going along, and there are connections where it's important, and that's the way that nervous systems of animals work. And it's not the way even deep learning systems today work.
That's correct.
They're struggling towards it to make things more parallel and all, but
Mm-hmm.
what's parallel is little von Neumann machines going around.
Exactly.
So that's progress, because at least people don't think of one single computing stream. Mm-hmm. Now it's that obviously highly parallel things do better.
Right.
And you've been close to a lot of that. But we haven't scratched the surface on that. And that's just what you get. I'm an amateur biologist, but just looking at nervous systems of animals and talking to your friends who do it professionally, there's no resemblance between the two systems. So there's an opportunity there.
Yeah. What he was doing was what we call neural networks today, mm-hmm. and
but in a more organic sense.
Yeah.
Yeah. Right now they're being emulated
exactly
on a digital system. So it's a big simulation they're trying to do, and the result is that it's a pretty lame emulation, because you want it to run fast and blah, blah, blah. And so, you know, it doesn't have that flowing nature like information in the brains of animals.
Right. Computers are just bad imitations of brains.
Oh, they're what people know how to do.
Well, they're all copying the brains of mathematicians, they think, but
well, it was a very small part of the brain of a mathematician that knew how to do those things. Mm. It was essential that they were able to do them.
Mm. Oh yeah.
But it's a very small part of the brain. But that was the part they would teach because they knew it.
They knew it, yeah.
So then that got to be what it was. Mm-hmm. And then
encrusted.
Yeah. So then, of course, Turing had this thing, well, any computing system can be as simple as this. Mm. And what's wrong with that statement is that your definition of a computing system shrinks down on that definition. Mm-hmm. And then there's no room for creativity anymore. Mm-hmm.
But of course, but that Turing machine insight really gets falsified frequently because they ignore the crucial conditions that Turing specified. You needed infinite printer's ink, infinite time and space. And in the real world, as Carver told me long ago, all parallel processing is intrinsically application specific. That the Turing machine can do anything, presuming infinite time and space. But we don't have infinite time and space, and when we define our domain, it becomes an application-specific machine.
Yeah, and it's they deny that because they say, well, I'll write a different program. No. This is it's a machine designed to run what programs you try.
Right, exactly.
And so that's the application. And for years they would deny that anything that had data flowing through it was a computer. It's very interesting. I was at DARPA one time, and one of the DARPA director at the time, we were having lunch, and he wanted to know about this, and I talked to him about how computation was done in the visual system of animals, how different it is.
Right.
And he looked at me and said, well, that's not computation. Because it wasn't what computers do. And in those days, it wasn't something computers could do. Probably still true in a larger sense. And I don't know what sense.
Yeah.
If you knew in what sense, you'd be off doing it.
Yeah. Well, to the degree that you knew, for example, I mean, your research on the human retina led to the Foveon camera that achieved stellar resolution, and George, you chronicled this famously.
The Silicon Eye. It tells the whole story of much of those parts of Carver's career.
And that whole Foveon thing was an idea of Toby Delbrooks.
Yeah.
And he...
transducer physiology.
Yeah. He talked to me about it, and I said, well, interesting, but I don't think it'll ever make color photography. And that's what Foveon ended up doing.
Exactly.
Because I was wrong.
Interesting. Yeah.
But I didn't shut him down. I said, hey, you want to chase that one? Chase it. Well, it turned out he was right on.
Tell me about your work with the cochlea and how that technology advanced hearing aid technology.
It was interesting. The models we built of cochlea were analog. And in that application, it was a big, the semicircular canal in the ear has a lot of sections. Each one has hair cells on it that half of them are sensors and the other half are amplifiers, mechanical amplifiers. So we built a model of that. And the problem of that model we built is that there was a long cascade of analog sections. Well, each analog section will inject a little noise and keeps adding up the noise. So the inherent noise in an analog circuit got multiplied by the number of stages. So that's not a possible way to do it. We learned a lot about hearing in the process. So that was one of those things that we learned a lot, but one of the things we learned was that's not the way to do it.
And what did Lloyd finally do? And an audience was a big breakthrough. Lloyd Watts was a student.
He ended up doing it in a way that didn't have things adding up. And eventually that ended up being a digital filter-like thing, but not one of the standard things that was known. So that was really a nice outcome without thinking about it as an analog thing. It hadn't been discovered how to do it. And so that was a fun thing.
And it went into all smartphones. I
Yeah.
mean,
Yeah.
Apple adopted it and brought in Lloyd, and then they really contributed the original Apple system for the smartphone.
Oh, yeah. Yeah.
Yeah.
Yeah. And then Apple did its thing.
Yeah.
And the company went bankrupt. And not quite, it got acquired. But a graceful way of going bankrupt.
Earlier, we touched on this idea of technology push, and I want to revisit that here in a little more detail as really one of your guiding principles. You know, and again, you see the fatal flaw in a market demand model. So by the time you've got a product, you're too late. All you can do is play catch up,
Yeah.
right?
Yeah.
So you prefer this technology push. Find an interesting new technology and find a use for it.
Yeah.
And that's worked for you. You know,
Well,
Yeah,
and if it doesn't work, it doesn't work. That's one of the
Learning
the-
process.
yeah, that's one of the outcomes.
Yeah.
And if it isn't, you're not being honest about the.
well, and the resistance that you get to that is in the form of, oh, that's a solution in search of a problem,
Yes, exactly.
Yeah.
right?
And as Peter Drucker said, don't solve problems. When you solve problems, you end up feeding your failures, starving your strengths, and achieving costly mediocrity. Don't solve problems, pursue opportunities, and change the whole landscape of your company, your project. The problems go away when the whole field is transformed.
Right. So, again, just your economics perspective. You look at John Maynard Keynes. He argued that demand creates its own supply. Okay. So, you would argue then that scenario produces an inferior result versus the idea that supply creates its own demand.
Yeah. Supply creates its own demand is called Say's law.
Say's law, yes.
And in Wealth and Poverty, I do all the permutations of supply creates its own demand, but clearly there's no demand, zero demand for novelty, for completely new products. The entrepreneur has to have an imaginative sense of the needs of others that aren't even articulated. So market surveys are steering by the rear view mirror.
Yeah,
And
yeah.
lots of companies do market surveys and demand surveys and or end up crashing because they're driving by the rear view mirror.
Exactly.
The future is always undefined, and supply is that is the supply of an innovation creates the demand for it, as Steve Jobs always confirmed that.
Yeah, yeah. And then it's one of those things where if you have something and you show it to someone and they say, oh, I've got to have one of those, then you know.
Yeah.
But that's the first time you know.
Right. Yeah. So tight correlations between technology push and supply side economics.
Yeah.
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 It's just a different view of the same phenomenon.
And creativity always coming as a surprise.
Right.
And information being defined as surprise, unexpected outcomes.
So as a pragmatic marketer, then when I put on my hat of a startup that's got to take this new thing to market, I'm very grateful for people like Everett Rogers, who defined the methodology called diffusion of innovations. You familiar with that? The diffusion of innovations.
Yeah.
Basically, I've got this novel, radical thing. How do I introduce it to the marketplace? And it's basically 5 rules. You know, you need to be able to demonstrate its superiority in some sense. Has to be easy to assimilate into an infrastructure. You have to be able to integrate it. It has to be easy to use, and people have to learn about it. Right? So you can take any novel technology, product, idea, concept, however radical, and introduce it that way. And people look at that and say, where's this been all my life? Right? And no market survey, again, would have ever produced that. No market survey ever indicated that there would be demand for a consumer Humvee. Right? And
Yeah.
yet,
And that's a well-known thing.
exactly.
Now you go out where things aren't well-known. Like the one I used to use in debating with Clayton Christensen was there was, you've been cleaning the floor with a broom, and then somebody comes along with a vacuum cleaner. Well, there hasn't been a vacuum cleaner. And it's much more expensive than a broom. But it's one of those things when people see it, they say, I have to have that. And then now you can be on the kind of learning curve that Clayton talks about.
Yeah.
But that leap is one of these things that you're talking about. You're on a different thing now.
In a changing world, you got to leap before you look.
Yeah. Well, and we do know that there are these generative markets, right? I mean, you've demonstrated that many times. You know, new products come about because this technology enabled it, right?
Yeah.
So Bill Davidow takes this even further. I love this thought of his. The physical world has no purpose. A tree did not grow to provide man with firewood. Rivers were not created to make it efficient to move goods to cities. Clever man figured out how to make those resources serve his needs. It's an interesting corollary.
Yeah.
I like
That's
that.
a good one.
Yeah. So, but now in the case of R&D, where things can be more speculative, you know, venture capitalists and other funding resources, they want to know up front, what's this thing going to be good for? You know, where am I going to find market traction, right? So isn't it hard to fund a technology first approach, or is that, you know, a particular luxury of academia?
It was much easier for really creative things of the kind that I know something about to be funded back in the 70s and you know, a bit into the 80s. I think it's much harder now because you have the piling on phenomenon. Venture capitalists want to do risk-free investment.
Exactly.
Which means we don't have basically any venture capitalists of the type that I knew with Art Rock and Gene Kleiner and Tommy Davis and those guys, where they would see that it's one of these things that, yes, we don't know that there's a market there, but you know, it kind of feels like there would be if we had one of these widgets. And I'm willing to bet on that. That was the old venture capitalist.
Right. That breed doesn't exist today.
No, I think they're gone. There are certain individual investors.
Angels.
I don't use that term because very often they're not.
Shysters.
But we still have some folk like that will see that there could be an important thing here, and it's worth finding out.
Yeah.
If you look at the investment that way, you know, this is I always say it's just tuition for finding out. You know? It's not.
Yep.
This isn't the investments that's going to make the money. It's the investments that's going to find out if there's money to be made. And that's, you know, that's not a dead species, but Heinlein has a real point that if you can pile on with somebody that's already shown that there's a market and that then that's a risk-free investment. And so why should I invest money on things that don't have those properties? Well, it's the innate curiosity.
Right.
If there were to be a thing like that and there were an application for it, then there would be a principled investment one could make. And I'm willing to take a bet that 1 time out of 10 we'll find something, and the others will find out that there isn't such a thing.
But in a sense, they too are listening to the technology. Right?
Yeah, yeah, yeah.
Following their nose there.
Yeah, absolutely.
And I think there are lots of venture capitalists. It's just they change. I mean, we rather abolished initial public offerings for most technology companies. Only the biggest ones now can have initial public offerings, and without IPOs, the whole venture model collapses. And a bill called Sarbanes-Oxley essentially imposes a $2 million toll on any company that goes public. All sorts of new regulations make it more difficult to be a public company, and so we now have these corrals full of unicorns, all supposedly worth more than $1 billion. But and this has been a somewhat stultifying model.
Yeah.
But at the same time, a company called Ethereum created the initial coin offering in the crypto space. And in the last 12 months, some $25 billion have been raised in initial coin offerings. And they're real startups, and many, and 46% of them are already went bust. But there are huge new ideas that are transforming the whole world economy. And I spend a lot of time in China these days, where my life after Google has been prospering. And that's my book. And
Well, you're a bestseller over there.
yeah. And China now has more IPOs than we do, 3-4 times as many IPOs
And a
as
shocking
we do.
number of unicorns as well, too.
And now more venture capital than we do.
Yeah.
So the different environments do have different results. And although China's is got a communist regime, they allow capitalist adventure and startups, and a real amazing startup culture over there. And if we have bad policy, capital moves to other places.
Does indeed.
And we have to keep that in mind. Venture capital has become a little stultified in the United States, but we need new models, and new models are emerging.
We have, as a culture, been drifting into the belief that businesses are leeches on the society. And part of that is because we have an education system that doesn't talk about the innovation. We should be teaching our kids about that above all other things. Across the entire culture, innovation is what brings us better life, brings us a more satisfying way to contribute to our culture. It's the very soul of the culture is innovation. And here we're trying to snuff it out with government regulation because, well, it might not work. If it always has to work, that means there's no progress.
No information.
No information. So we're seeing the result of the fact that our education system has given everybody the wrong idea about how prosperity comes about.
Yeah.
It's your point again, this zero-sum vision, where everybody is obsessed with the scarcities and fails to see the abundances.
That could yield from innovative thinking.
Yeah. Yeah.
Creative abundance.
Yeah. So, when you expose our youngsters to a model of a society that's zero sum, basically,
Yeah.
you end up with kids that want to contribute, they want to create, and it isn't in the model.
No.
And I find it very painful to watch this. As a teacher and as a student in a one-room schoolhouse, there was none of that then.
No, not too much.
And so it all looked like opportunity. And,
Yeah.
Pursuing opportunities.
Yeah. Well, I want to talk about another way to pursue opportunities through innovations, maybe existing innovations, just different ways of combining them in different ways. For example, I mean, there are many trends that emerge from the combination of completely disparate, otherwise unconnected technologies that originated and evolved, independently in isolated application spaces. Okay? So this intrigues me, this notion of how we connect these things up. So if you imagine for a moment GPUs, digital cameras, the Internet of Things. Okay, each of these again developed in standalone applications in their specific domains, spanning gaming consoles to home thermostats. Right. Now, so in this milieu, let's throw in LiDAR, machine learning, an array of sensors and different kinds of actuators. Right. No doubt now you're already thinking self-driving car. Right. So the self-driving car would not be possible without all of these technologies being integrated into it. So it is in fact an irreducible complexity, yet none of these constituent technologies foresaw their application in something called a self-driving car at the time that they were conceived, developed in their respective markets. So while it's easy to look back from the viewpoint of that self-driving car and connect all the dots looking backward, okay, how do we connect dots looking forward with all the technology that's on the horizon?
Well, the Chinese strategy is they say real self-driving cars aren't really possible now. So unless you build cities for self-driving cars, so they're modeling the whole city to accommodate self-driving cars using the technologies that are possible or in prospect today. And I think the model of self-driving cars based on machine learning is quixotic. It's not going to work. All the combinatorial explosion of possible contingencies on a road in San Francisco or around the country is just not something that can be learned by looking in the rearview mirror of a machine learning program. But it is possible to radically improve LiDARs and make the sensory system of the car far better and faster. It's possible to make the car itself into a little AI database and of a different kind. And you can have self-driving cars that are distributed and with local intelligence and which actually can work. And there are lots of different ways to approach this game beyond the original Sebastian Thrum paradigm that has been adopted by much of the industry in the United States and is not really proving as fruitful as it could be.
So you're a bit skeptical that we'll go beyond, in a practical sense, like level 3 automation.
No, I just think there are different ways to do it. It's going to develop in all sorts of unexpected directions. Clayton Christensen notices that essentially in most cities now, a certain proportion of the cars, as it were, are little electric, essentially go-karts or whatever from golf courses that are moving into the streets, and they're disruptive technology. There's going to be many different paths, and the idea that the self-driving car is going to be a single, all-purpose, magical vehicle based on AI, I think is misunderstands the problem. And I get this argument mostly from Austin Russell, who started a company called Luminar at age, he was a Thiel fellow lured from college to start a new company. And he's predicted most of what's happened, the failures of various self-driving cars, the deaths, the revulsion against them, and the need for new thinking and fundamentally better LiDAR technology, and that's what Luminar is doing. And other companies are now following this path.
So, I mean, the Chinese have a better idea. They're taking a more holistic view of it, because you can't look at the self-driving car in isolation. It's got to be in the context of all the other infrastructure. And that's abjectly missing, obviously.
I think it's missing. We have a faculty guy here at Caltech who's systems type person. His background is in dynamical systems and analysis of them and so forth. And he did a very interesting study, just himself. He posed himself the question, if what your goal is to respond maximally quickly to an unforeseen situation, how would you design your system? Now that's a very good description of a system that has to drive a vehicle, because you rarely have to use that. But if you don't have it, we would all be having accidents all the time. So it isn't what you do most of the time, it's the exceptions that really determine whether it's a workable technology. So what he is able to show is, if that's your goal, the way you design a system is you put most of the intelligence out at the
edges,
at the inputs and outputs. If you look at any living system, that's the way it's built. You got huge amount of neurons and ganglia and all kinds of stuff in the periphery. Your sensors and your muscles are essentially one organ. When you're playing tennis, you don't go back up here and say, oh, that ball is blah, 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 therefore what I should do is I should move this elbow back and on. And you wouldn't even be able to play the game, let alone get good at it. So that has, you see, we're stuck in the same thing we were when I first started thinking about.
Right.
We had the great big computer, and it was a central thing, and everybody came to it. And that's not the way living systems work. So living systems are alive today because they were able to survive in an environment where there are a lot of surprises. So what are we doing? We're building systems that aren't very good unless it's something they've seen before.
Touche.
So anyway, I'm glad that there's someone from a theoretical perspective that figured that out, because now maybe people, maybe academics will pay attention to it.
Well, I'm almost afraid to ask what you think about the singularity?
Well, I think Ray Kurzweil is a good friend of mine, and he is, and the singularity is a great vision that allowed him to organize all the technologies and dramatize this learning curve model that's at the heart of my information theory of economics. And I think he's great. I think he himself actually is less committed to the kind of mechanical singularity where machines usurp human minds than some of his followers are. I mean, he's quite a flexible and interesting mind, if you know him.
Yeah.
So, but I don't think the singularity is right. I mean, it's machines are not going to usurp human beings. Minds are not computers. Computers can't function without minds. So I don't think Ray is right about the singularity in those terms. But on the other hand, he's not sure he's right either. So I think he's more sophisticated than many of his followers in this field.
I sort of look at it as utopian vision is wonderful because it is inherently creative and futuristic and positive.
Yeah.
And I think in that sense, it's wonderful. The fear part of it, you know, ever since we've had computers, we've had that.
Mm-hmm.
That, they're gonna take over the world, and we've had all these movies about computers.
But this is different.
Yeah, exactly. And to me, you know, every new technology has met with, I mean, that's one of the things I get met with, the fear.
Yeah.
Oh, it can be used for all kinds of evil things.
Mm-hmm.
Every technology can be used for good or evil.
Technology is benign.
Yeah. But history is such, and you don't hear this. Probably they don't even tell our kids about it. But actually, life for every human on the planet is better now than it was 100 years ago or 50 years ago.
Even if you happen to be very well off 50 or 100 years ago.
Yeah.
A king.
Mm-hmm.
Yeah. And violent crime is down.
By every measure.
And, you know, everything about life, even in the poorest countries, is vastly better than it was 50 years ago.
Yeah.
But this is not the singularity, the end of the line. I call this Google Marxism, where you believe, you make the same mistake Marx made. Marx's big mistake was to believe that the railroads, the steam engines, the looms, all the apparatus of the Industrial Revolution was the kind of final human attainment. That in the future we wouldn't have to worry about producing wealth. The only issue would be redistributing wealth. And today the Google people make the same kind of error, Google and lots of other people, that AI, machine learning, search engines, algorithmic biotech, robotics, all these technologies, they're kind of a final thing. And they not only obsolete human labor, but human minds even. And this is a repetition of the Marxist error, that now the only issue is redistributing wealth rather than creating it. And the fact is that we're opportunities are larger than ever, and there's no prospect of machines taking over and no prospect of machines usurping human minds and destroying all our jobs. It's just, it's a delusion.
Well, and what went with that was that the sort of enforced top-down management of the whole process would give us this wonderful utopian thing. And what's happened is, what's given us the progress is free enterprise. And governments have often gotten in the way, but have rarely contributed in a positive way. It's the individual creative minds that have often, in spite of the very well-meaning people who are creating things like Sarbanes-Oxley laws that prevent
Right.
smaller companies from functioning as public companies and so forth.
Fair disclosure, where all communications from the company have to be channeled through the lawyers and PR people.
Yeah.
Well, so let's wrap up here with a bit of a lightning round on where these creative people are going to take us in the next 50 years. You want to venture this? Computing. Where are we headed?
Well, let's contrast with where it is right now. Where it is right now is we have a new algorithm, which isn't new. It's from the early 80s. And we call it machine learning, and it's a big rage right now. And it uses slightly generalized stored program computers. And there's been progress there. So that's going to go on. But is there something we can see? Well, one thing that we know from the last 20 years is that applications will spring up that none of us thought of. None of us thought of Uber. You know, it's obvious once you see it. I didn't think of it. Gordon Moore didn't think of it. So it's obvious that there's going to continue to be a lot of innovation in the application of technology that will then drive learning in the process of just those technologies will get better. So that's a synergistic cycle. And as those technologies will get better, people will see ways to use them that create value.
And surprise.
And surprise, like Uber did. I saw, why didn't I think of that? I could tell you, I didn't think of the cell phone for one reason, that at the time when I was doing the VLSI thing, there was a Supreme Court consent decree that said that IBM could have computing and AT&T can have communications, and never the twain will meet. You don't get smartphones that way.
It's an intriguing example.
That's what I thought. I thought we had such a stuck government that it would never happen. And I was wrong. I was surprised. And guess what? So once there's been a big surprise, you can trace it back to some people who said that. But they probably said a lot of other things that didn't happen.
They didn't pan out so well.
Yeah. So my feeling is that we're still open to a lot of innovation. We don't know what it's going to be. Like you have this milieu that we're living in. It's got all these technologies. They've got some pull now to make them better. That's why I've been positive about self-driving cars, not because I think they're going to be, in the present concept, they're going to be you know,
Ubiquitous.
yeah, they're going to be special purpose and they're going to live in places that have been set up for them and that sort of thing. The most obvious one being you could fit up any freeway with signaling wires and stuff, and so you could have it set up to where that would be a very safe way to have a self-driving vehicle, because it's largely all set up on a rote situation. You have to be in this lane in order to turn on this out, and all that. So just the practicality of having people drive on a freeway has already made it pretty regimented, and make it a little more regimented so it can encompass self-driving things wouldn't be that hard. Take any random city, that's a different story. But I think what's going to happen is that all of these component technologies and system technologies and stuff are going to be contributing. And then somebody's going to say, ooh, it looks to me like maybe if I put that idea with that idea and use it for something like that, that'd be new.
Yeah,
And they're going to try it.
exactly.
And 90% of them are going to die, but that last one is going to be one of the answers to this question you just asked. So, to me, it's a process. It isn't a thing you say, it's going to be blah. No, it's not like that. It's a process, like the experiments I described. You don't see the end from the beginning. You just don't. You fumble your way there. And then all of a sudden it click, ooh, that's neat.
The eureka moment.
Yeah, yeah. And that's why we're there, we humans. You don't replace that with a machine,
Yeah. Yeah.
because the machine's a finite thing, and somehow we have indefinite boundaries.
Yeah.
Somehow.
It's a determinist machine that
Yeah.
prohibits surprise almost by its very intrinsic nature. Well, our nature is to look for surprise, and moonshots, as
Moonshots,
you
yes.
call them in your wonderful book, moonshots, and I think we're going to have a lot of moonshots, but they may come from sites and launchers outside our current ken. I think a lot of them are going to come from the new blockchain and
We
cryptocosmic
get into that.
pursuit that address two great current crises we face. The breakdown of computer security is, 1 billion breaches last year. The more money we spend on computer security, the more breaches and hacks occur. That's a failed model. There has to be a new architecture for security on the internet. I think it's the blockchain or some derivation of the blockchain. There's a new model for money. The more money we print, the more money floats, the more government central banks borrow or issue, the slower world economic growth is, and the more trade conflicts occur, and the more a sense of futility and conflict arises. And again, the solution to that problem also comes in the blockchain. So we have a kind of unity where this new path can both provide a new computer architecture, a new internet architecture, which is intrinsically secure, and a new world monetary system that restores the kind of global money that we became used to in the gold standard during the years when much of world economic progress actually occurred.
And it's all connected. all the way back down to the creative entrepreneur working in a
Yep.
lab on a big
Yep.
idea.
Yep.
Yeah. So what's next for you?
Right now, I'm working with a colleague on understanding the nature of superconductivity better and doing a bunch of experiments, and we never know exactly what experiment we'll do the next day, but depends on what we learn today.
And you'll follow that wherever it leads.
Yeah, yeah, it's great fun.
Yeah,
I'm having a blast.
that's awesome. That's great.
Okay, how about you, George?
Well, I'm going to be launching a whole bunch of newsletters and guiding people's investments in this perplexing predicament that the world faces with this collapse of monies and the feeling of hopelessness and trade wars. And I think we need to channel investment in different ways. And I think there are a lot of wonderful opportunities out there. Don't solve problems, pursue opportunities, and that's what I'm going to be doing.
And perhaps at some point it might intersect with superconductivity.
Absolutely. My daughter has been writing a book on superconductivity, inspired by. She also wrote a book about quantum entanglement, so she's prepared for difficult problems, and
A best-selling book.
yeah,
Quantum entanglement.
one of the top 3 science books in the New York Times list in the year it came out, The Age of Entanglement.
Fantastic. Gentlemen, this has been very enlightening. Thank you.
It's a lot of fun. Thank you.
It is.
Thank you.